properly now? I saw a message that you can't hear us properly. Okay, I can see Anslem Adedayo. Welcome. I hope everybody came with their notes. We are learning from some of the best in the world at this. Yeah. So we have Evelyn from Abuja, Omodolapo from China, Sharon from Lagos, Victor from Ogun State. Okay, Olawale, I know you.
Welcome, Alawali. Welcome. Welcome.
Abel is my colleague. I know him too. Welcome. Uh, I've seen Suleiman from Ibadan. I think I know Suleiman from the boot camp. I'm not sure. Collins from Makodi.
Let me talk from Ogun
David.
State. Well done.
David, Senna is not your real name. I know you too.
So we have 1 more minute for the introductions, and we'll just get right into it. Thank you, Sandra, for joining.
Okay.
Great, great.
Cherry, thank you for joining. Okay, so ask your friends that you registered together. The guest list was way bigger than this. We had more than 150 registration. So ask your friends to join in. Ayobami from Ileife, you're welcome. So we are live. Our plan is not to keep you. Oh, okay. Oliver, that means it's you and Sekou for the entire schedule. We are wishing your colleague well. We'll miss that. We were looking forward to that. Okay, Ahmed Olawale, you're welcome. Okay, participants are increasing. We had more than 150 on the guest list that got invited for this. So, okay, it's looking much better now. Olorun Toby from Lagos, you're welcome. Bayo from Lagos, you're welcome. Okay.
Okay, so you're looking ready to go. So um, thank you very, very much, guys, for coming. We're just gonna start um, the whole training session right now. We're gonna go ahead and just start. You already know what it is. Today is reinforcement learning masterclass in partnership with IBM, and we have our instructors already on the call. So we're just gonna start the call. Please make sure that you use the chat room in case you have questions. Feel free to drop the questions in the chat room or in the question and area center, and then we'll take note of it. And then, so if you have questions specifically, just drop it in the Q&A session so that we can always get there at the end of each session. We would have time for um, would have time for a brief introduction, a brief question and answering session before we move into the next session. So I'm going to basically start with a basic introduction of. I know that a lot of people know what that science Nigeria is all about, but I will still start again for people who are joining us for the very first time.
And people will be viewing on YouTube.
Exactly. The people who are joining us for the very first time, and then this video will be uploaded on YouTube after this, and so that people would also find the video afterwards. Will be able to understand what we are all about at Data Science Nigeria, and so Data Science Nigeria is enough for profit. We are the biggest um, learning AI learning and solution delivery network in Africa. It's not just something. It's not a self-acclaimed title. It's an award we actually won at the Deep Learning Indaba 2019. Deep Learning Indaba is actually one of the largest gathering of data scientists, both practitioners, researchers in Africa, and that's where we won that award in terms of the level of impact we've been able to make with all our channels of learning and impact. Apart from that as well, we've won several awards and made a lot of impact across different spheres, especially even on the global stage. And this one of the research paper won best poster award at the conference on economics and competition, and we were one of the non-academic institutions, and yet we still came top. We had to compete with academic institutions like Harvard and that, and then we still came up top, just to show you the level of competence that we've developed when it comes to knowledge and research. Also, this is DSNB recognized as the world largest AI hackathon that was held in Tunisia in 2019, just to show you the kind of global reach and relevance, not just operating at local base in Nigeria, but also reaching the whole of the continent of Africa, and also making sure that our works and our inputs have been felt felt around the world. This is also a co-founder been speaking at the world number one scientific AI platform, that's Triple AI in the USA. And this is one of some of our works also been captured and recognized by the World Economic Forum. Based on the work we did during the COVID-19 lockdown. Like we said, we can all be locked down, but that shouldn't stop learning and development across board. And also, these are one of the major work we also do regarding democratizing the artificial intelligence knowledge across. And this is one of the major things that we've also been able to contribute to the ecosystem in terms of putting all the best learning videos, tutorials, data sets together in a knowledge box, because a lot of people do not have access either to the internet or do not have access to this internet power and all this. So we try to democratize our learning by putting the best videos, learning videos from the top universities, MIT, Harvard, and just gather everything into a knowledge box, and we distribute it for free, completely free of charge, to about 30 different cities across Nigeria. And this is the second iteration of that as well. And also, these are learning channels. We run the biggest AI learning program in Africa with 30 unique platforms, which involved face-to-face, online, offline, across different segments. We cover beginners, kids, and teens are not left out, intermediate to experts, university students, professional, and C-level learners as well. And this is pictures of our learning communities across different cities. Our goal is that we make sure that AI gets everywhere and anyone can get access to this learning. So these are also pictures from different learning communities around Nigeria. These are also and mind you, all these trainings are basically free. You just enter into the learning register and enter in this learning venues and just pick up the learnings. Okay, we also are very, very big on developing the next generation of AI talent, and that's why we've been able to build learning clubs across 17 universities and 23 cities in Nigeria. And these are learning programs completely free, covering different levels of learners. Also, like I mentioned, children are not left out. We literally believe that for us to be able to reach our goal of 1 million AI talent, we also need to begin to involve our kids even at a very, very young age. And that's why you could see pictures. We also get to bring like events like this where we invite global, highly reputable hands-on data scientists to inspire, motivate, and just mentor learners. And this is one of those pictures where we invited several one of the leading, so just an event like that, you'll be meeting global data scientists like this again on this call, and then you also have the opportunity to communicate with them. It's just to be able to put these people right in front of you. They can inspire you, they can guide you along your journey to becoming a world-class data scientist. Also, our cream de la cream, we call this cream de la cream, because one of the most impactful um, learning sessions that we have called AI Bootcamp. We organize it once every year. This is where the best of the very best data scientists gather every year, and we bring in the top data scientists in the world to come and mentor them. I hope you can hear me. I'm seeing people saying, please, your volume is low. I hope you can hear me. I'm on top of my voice right now. I hope you can actually hear me. So this is where we bring in the best of the very best data scientists in the world to come teach, mentor, and guide students. It's always very, very competitive. Last 2 years, we had about close to about 2,500 people apply, and we were only able to select just about 250 people. And the reason why is that it's very, very competitive. Right? It's very, very competitive, and we have the very, very best data scientists also who come to mentor people at the boot camp. Also, one of our engagement also is that countries like China,
are investing in the education of the young people, inserting AI into the curriculum. And we feel like the continent of Africa must also not be left out in this kind of development. So we wrote the very, very first book, artificial intelligence book for kids in both nursery and primary schools. So you could get access to those books, and the links have been shared. You could just purchase this very, very first book for um, nursery, primary school and secondary school students in Africa. Right, it's written by a founder. You can also see the book getting endorsement for I prefer that scientist. That's Dr. Yoshua Ben, Prof. Yoshua Benju. Also endorsing the book, so you can see some pictures. Just make sure that the content are captured and really, really contextualized for kids to actually learn. Make it in a fun way and a very, very exciting way for kids to learn. And so very, very easy. You can pick up Python, pick up, and these just to basically institutionalize the learning for kids and in primary and secondary schools. And also, we just didn't just create the book; we also distributed the book for free to teachers. We organized a masterclass to train the teachers on how to begin to disseminate this knowledge to their students, and you can see pictures of that. And still an ongoing venture where we still train teachers and also run this for kids. Also, our AI clubs also are involved also in trying to educate the next generation of data scientists as well. So you can see us distributing the books and teaching that. Also, we're not just about capacity development. We are also about actual AI for good application. So we've developed solutions ourselves. We consult also for organizations and then solve real life problems. These are some of our solutions. Market Health Check for me that solve the problem of debt of data, especially in the Nigerian ecosystem, to actually solve real life problems. So you can see also creating a problem, creating a solution to actually crowdsource data. That's one of our solutions in the market. Also, we facilitate research. Partnership with the Innovation and Research Unit of the University of Lagos. This is also another research, another um, application. Also won like the best paper on fraud detection at deep learning in Daba. So these are some of the solutions. So we're not just big on capacity development, but the real life applications of this solution. And during the COVID-19 as well, not just when we say AI has the potential to basically change things and really solve problems, we also put our mouth where our money is. And then during the COVID-19, we were able to as well um, contribute to how the whole to our own quota to actually making sure that we properly manage the pandemic. And this is one of our solutions that we also developed in making sure that the isolation centers are actually adequately and properly positioned to actually help people. And this was based on using what we call the social vulnerability index alongside with geospatial data to be able to give an informed decision based on data on where the isolation center should be placed, especially areas in Lagos. And also, this is also our SARS and Ebola virus paper, trying to compare and trying to make sure if we can find insights from previous diseases that Africa basically encountered, and now we can use those learnings as well in the management of the COVID-19 pandemic. So these are some of the other research that we're currently going. So we also have a committee of practice development. So we don't just want to develop but we want to develop an entire ecosystem that facilitates learning and development. Okay, so I'm going to round up here, and these are things that we do. We run a professional training program to educate people who are looking to transition into the field of data science can also begin to learn. So these are our professional courses. I'll just rush through this. We have proper engagement with Butner Foundation, Bill and Melinda Gates Foundation, Mastercard Foundation. These are people who have seen our work and been able to endorse us. So these are trainings contributing to national development, to professional development. And I will stop there and then we go straight into the business of the day, which is actually our reinforcement learning masterclass. We're so excited. Our partners from IBM are also very, very eager to really make sure that we contribute to the development of AI talents in Africa. So our
Yeah.
very, very first instructor for today, I would would you like to introduce the first, or should I just go ahead?
Oh, I wanted to tell the participant that there's a question from Sekou already in the chat window.
Okay.
So yes, there are questions for the attendees. This is supposed to be like a continuation of some of the things that were discussed at the boot camp, I guess. So if you're on the reinforcement learning Slack channel, have you written anything recently? So that's from Sekou to you. So you can introduce and then he can start his class. So
Okay.
question for the participants in the chat window, kindly look at it and respond if you can.
Okay, thank you so much. So you have a question, so feel free to respond on the chat to Sekou's I hope I'm pronouncing the name well. Plus, feel free to respond to his question. So our first speaker today, Sekou Remy, is a research scientist and technical lead at IBM Research. Is excited about developing appropriate technologies which will transform Africa and the world. He's also a proud alumni of the Georgia Institute of Tech and of Morehouse College, both in Atlanta. And so it would lead us today and take us on the topic: when is it a good time to consider reinforcement learning? It's a privilege to be able to welcome you, Sekou. So you would have the floor. I'll stop sharing my screen. Thank you so much for making time out to really take our students in this topic. So over to you, Sekou.
All right, so before I start doing the presentation, I just wanted my colleague Oliver to introduce himself. I will introduce myself and then just keep running.
Okay.
Fantastic. Yeah, thanks for that, Sekou. So yeah, hi everyone, my name is Oliver Bent. Also, we'll give you a talk after Sekou, but so that we keep things moving. So my background's, we've been working together with Sekou for the last few years on applying reinforcement learning to challenges in sub-Saharan Africa, specifically focused on epidemiological modeling, which you'll find sprinkled throughout our talks. But generally look forward to sharing an aspect of machine learning in Bayesian non-parametrics and how we've used this in some of the reinforcement learning problems that we're going to talk about. So great, over to you, Sekou.
All right, so if at any point in time you have questions, please feel free to drop those questions in the chat. When I'm presenting, Oliver will help me, and when Oliver's presenting, I'll help him so that we can make sure that we can catch your questions as soon as they come up. So as Oliver, as you know for the outline, there are 3 sections, and Oliver and I are going to cover them today. So just so that everybody can be on the same page, I do still have materials which I have added a little bit. So that if anybody wants to dig a little bit deeper on their own, these are all free resources that you have access to. Just an internet connection is needed. Really nice resources in that they are very accessible from the standpoint of pointing you in the direction of all of the other things that you could get into if you're interested, or allowing you just that introduction. So tasks, concepts that I think would be useful for you. This normally is a question that people have: where do I get more information? I want you to see it up front. The other piece is that, yes, this is in essence following on with the conversation that we began during the boot camp. But I do recognize that everyone was not present at the boot camp. I know that the recording is available, so you can go back and check, but I'll at least cover, let's say, 4 or 5 slides of background material of reinforcement learning. So here we go. The bigger picture that we're looking at is reinforcement learning sits within the universe of machine learning. Machine learning we're familiar with. They're tasks that we're comfortable with, very comfortable with, I know. Classification, regression, ranking, clustering, dimensionality reduction, translation. These are things that we are very, like when you think about machine learning, those are the things that are normally top of mind. The broader picture, though, is that machine learning is itself composed of 3 elements, and that's the supervised, unsupervised, and reinforcement learning. And it is situated within the universe of AI, artificial intelligence. There are other facets of AI. So whether we talk about reasoning, AI is broad. But this is normally, when we're talking about reinforcement learning, this is the third leg of that stool in machine learning techniques. Specifically, reinforcement learning is all about learning from interaction. You have to interact with something, as opposed to supervised or unsupervised learning, where you're, in essence, you can say you're interacting with a data set. Sometimes in the supervised case, that data set has labels. Reinforcement learning is different from that because you don't necessarily have labels. You're interacting with an environment and learning from the signals that are contained in that environment. It is goal-oriented. What does that mean? The algorithm or the agent that you're writing, it has a purpose. It has something that it's trying to do. And we'll talk a little bit more about that, but briefly stated, its goal is to maximize reward. How does it do this? It learns about, from, and while interacting with an environment. So I said, unlike the case of supervised and unsupervised learning, you're not training by using a data set and do a train test split and then do a validation or do whatever. In this case, you're interacting with an environment, and depending on the type of RL algorithm that you choose to implement, you can either directly be interacting with that environment now, or maybe you can capture history about someone else's interaction with that external environment. And the goal as an RL agent is to learn what to do. So this is the picture of reinforcement learning, right? Very different from the other two elements of machine learning. The learner doesn't explicitly get told, this is the action that you are to take right now. The learner has agency. It can choose whatever actions it would like. And hopefully, when it takes new actions, it is able to learn things about the world. But if it takes an action that has been taken previously, maybe it's confirming something that it knew about the world. There's an element of trial and error which may be captured also it may be familiar to us, because if we think about human development, there are things that we try and we learn new things. Right? So this notion of a trial and error exploration of our environment, this is something which is a part of reinforcement learning. It's also possible that you can have a delayed reward, meaning that you may forego something that you could, a reward opportunity in the short run, because you know that it would lead to better long-term outcomes, right? So there's a trade-off of, do I do something now and get a little reward? Or do I wait and do another action now so that I can get more reward later, right? Trade-offs. The trade-offs that we are already familiar with in the other domains of machine learning are exploration and exploitation, and that exists here as well. But the frame to think about this is, reinforcement learning is a little bit different from the other types of machine learning techniques, because you're really thinking about an agent as an entity that has a goal, and it is interacting with an environment. It's not just solving an element of the problem. The agent has the entire problem in front of it. In essence, what that means is, when this agent is interacting with the world, any element that it needs to learn, it has to learn from interacting with that environment. There is no help coming from another source. The agent exists in both space and time. So what it does at a particular time matters. So for example, if you think about, I'm laughing because I'm thinking about this for myself. What actions you perform. So if you are sitting in a chair, if you decide to stand up, that outcome would be very different from if you were already standing. You can't stand up twice if you were already standing. So if you had forgotten that you were standing, for example, and you choose the action stand, there might be a little bit of confusion because, hey, wait a minute. I did an action and nothing happened, nothing changed. So this concept of what you're doing at what time matters. That's why if you look at the figure, action has a subscript, A sub t. But you're continually learning and you're continually deciding which actions to perform. And you're continually observing how your actions change the environment, or what effect or what affects your actions have on the environments. Right? Now, the environments in some cases have noise. So this notion of stochasticity is something which is very welcome in the context of reinforcement learning. A brief list of the items. When we talk about RL, concepts like policy, reward, value, model, and I've added state and action are things that we need to understand. So the policy allows you to understand what to do. So for example, if you're in a given state, what action should you perform? The reward allows you to get a signal or a measure of how good a thing is. So if you were playing a game of tic-tac-toe and you won that game, then the actions that you executed were good. But if you were playing a game of tic-tac-toe and you lost the game, then the actions that you executed were either not good or less good than if you'd won. There's a notion of value. It's not directly reward, but it gives you information about how good something is because it will lead to the reward. This concept of a model, I didn't really go into depth the last time that we talked, but there's a notion of if your agent, your reinforcement learning agent, is able to build a model of the environment, then it can use that model to learn things, or it can use that model to develop a mental map of what the environment looks like, what relationships exist between states and actions, and where great rewards may lie. But all reinforcement learning algorithms don't include this component of a model. So there are some things called model-free reinforcement learning. But if you had a model, it would be really useful because now you can use that model to determine, better determine, I would add, what actions make sense. So the last time we had this, one of the two examples of the applications that we talked about was in the domain of malaria. And in this concept, you had a model which allowed you to encode domain information from epidemiologists, bioinformaticians, etc. People who know something specifically about either the disease or the vector or the context in which the disease is spread. So that model is something that was then used as an input. That model was calibrated for a particular location on a map, a particular space, because one location may have dynamics or characteristics that are different from another. And in this case, so here we have a person sleeping under a bed net. So basically, instead of looking at all possible interventions, we're only limiting the interventions to just two, just so that we can have a conversation. Or this was done so we could have that conversation back in November. But in this case, we're looking at two potential levers, two potential interventions that you could have done in a particular location that would have an effect on the prevalence of the parasite responsible for malaria. So as an example, if we deployed bed nets to 50% of the location, in this case it's Tororo in Uganda, and we deployed 70%, we sprayed 70% of the homes with indoor residual spraying. According to the model, over a 5-year period, this is what would happen to the prevalence of the parasite. It would go down. Different models may project different things into the future, but the point is, the model allows us to quantify what would happen and specifically what would happen over time. So in the context of reinforcement learning, we showed how these models can be used to inform an environment that an agent can now interact with, right? So we're talking now about reinforcement learning applied to this domain in a healthcare setting, public health, and the agent is seeking to learn what interventions to perform by interacting with the model. A question that a decision maker, or a question that may be relevant in this context might be, over the next 4 years, how do we drive the parasite prevalence in all of the locations in the country to 5%? So I just showed you a picture of what that projection looked like with one intervention program, meaning we can say one action, and we would see what would happen over a 5-year period. So that particular intervention in that one location allowed the parasite prevalence to get to less than 5%, which is the goal. But now in the context of reinforcement learning, the question is, was that the best sequence of interventions that you could have performed? Is there another sequence that actually would have been able to get there with, let's say, less money, or get there by using less resources, or get there in a manner that was equitable across the entire nation? So these are different problem formulations which we can talk about. Now, if, and I know that there are many of you in the room, so let's see if you can use your thumbs up, if you can figure out where that response is on Zoom. So if you were thinking of this framing of a question, how would you drive the parasite prevalence in all 134 districts to less than 5%? And you were given a model that allowed you to understand, for a given action, what would happen to the parasite prevalence over time. What might be, would a good example of a reward be the following? So I'll give you, you can put a thumbs up if you think this is a good example. And the first is this. Would it be a good reward if you just, if you got to less than 5% at 2025? That's the reward. So you get a very large positive number if you get to 5% by 2025. Let's see what the participants say. So I'm trying to see if I can catch some thumbs up. So I see 3 participants, 4 participants saying that sounds like a good thing. All right, there are 97 of you in the room. Does that mean that the rest of you say that getting a large positive reward if you got to 5% at 2025 is bad? Is that what I should interpret? All right, let me frame it another way. What if you got a positive reward every time in a given year you reduced the prevalence? So if your prevalence was 9% in 2021, and in 2022, you reduced your prevalence, doesn't matter by how much, would that be a good reward? Okay, different hands are going up this time. 5, 6, 7. Okay, so people are generally thinking that this is a better reward. What
yeah,
I'd like
in the chat, Sekou, people are agreeing with you.
Okay, awesome, thanks. But what I want you to think about here is that depending on how you frame it, different plans or different actions or different sequences of actions may actually end up getting different values, different reward values, depending on what this reward function looks like. So we have decisions to make. How do we want to represent what is good? Right? Now, the states one is pretty easy since I've only shown you one state. And in essence, that state is the parasite prevalence at a given time. But there are other ways that we can represent that information. Maybe we can say the state is binary. Are you at the target or not? So in essence, we would convert a graph like this one to everything that is below the threshold would be in one state, and everything that is above the threshold would be another. That's a different representation of the state of the environment. Right? We have freedom. We have the ability to control what are those states, what are those rewards. In many cases, the actions are defined or pre-specified for us. Right. So hopefully that at least brings those who came later on board to this notion of reinforcement learning with a concrete example from the last time, just to refresh your memory. But the question that we're asking right now is, can you really think about any problem? Can we always apply reinforcement learning? Well, I hope you, just the fact that we're actually having this conversation after I was so gung-ho about reinforcement learning in November, I'm asking this. We have to manage our expectations around the applications of these kinds of algorithms. And in this context, we have to think about when is it that we can actually apply RL to problems. So the first thing that we need, and for those of you taking notes, you probably flipped back quickly to this, is this concept of an environment. Right? You have to have an environment. And in that environment, assuming that we are given one, let's say from a problem, there must be a reward function. If you don't have a reward function, you can't apply anything from an RL context, right? This reward function must have a strong signal, meaning that there's something that you can learn from. And the design of the reward function is tricky because some reward functions may allow you to get positive reward for a series of actions that actually don't make any sense. So for example, and some of you have probably seen these on YouTube already, there's some agents that are able to maximize reward. And you look at the actions or the sequence of actions that they're performing and you're wondering how. So for example, if you're supposed to stack blocks one on top of the other, but your agent learns that if it flips a block upside down, it's able to get more reward than if it stacks the blocks up one on top of the other. That's an example of a reward function which may be valid, but doesn't necessarily provide the output that you expect. The algorithm doesn't care what we think. All the algorithm is going to say is, how can I fulfill my goal of maximizing my reward in the long term? as a team, so Oliver mentioned that we've been working in this space for a little bit. Our approach is actually a little bit, I don't know if you'd call it cheeky, but since we're talking about solving a problem or trying to support users, our approach is to say, let's talk to the users and understand what is it that they believe is good. So how would they evaluate an action or a sequence of actions and the outcomes associated with it? So they may say, I care about things, good things are things that are cost effective. Or they may say something like, if we can minimize deaths, that is better than having something that is cost effective. So the users have an understanding of what is good. So by speaking to them, we have the ability to quantify or codify what that reward function should look like. So we don't, as machine learning practitioners, we don't have to invent things ourselves. There's also in this environment, this notion of action and observation spaces, i.e. what things you can possibly do and what observations you can possibly observe, you can see. I use the word reasonable here, and I have it in quotes for a reason. There's a concept of, we know that it can be noisy, but we would like it not to be too noisy, because if it's too noisy, then it will be difficult to understand the relationship between any action taken and the observations observed or the rewards received. Dimensionality is a really big deal, especially when it comes to us trying to implement. So Ibrahim, I remember you from last November, you were asking, hey, what compute equipment do I need if I want to do reinforcement learning? Well, if you have very high dimensional action spaces or observation spaces, you may start creeping into the domain of, I need a GPU to get things done. But if the dimensionality is more manageable, let's say on the order of, let's say maybe 10 or 12 or 15 dimensions of either action or observation, maybe you can do these things in CPU land. This concept of transition probabilities, for those of you who have experienced Markov decision processes, you can do a little bit of background reading on those. The transition probabilities allow you to build the relationship between, if you did a particular action at a given state, what state do you go to next? So what's the probability of going to state 1 versus state 2 if you did action A? That transition probability, that matrix, if there is a lot of noise in that transition probability, then it can be a little bit on the unreasonable side. And then finally, it needs to be easy using the environment to generate what we call relevant experiences. So if it takes an hour to run or to evaluate one action, that's very different from if it takes 15, 20, or 30 hours to evaluate an action. Machine learning in general has this question about, do you have enough data? Can you train long enough? Reinforcement learning specifically has a challenge around sample efficiency. So how many actions do you need to evaluate before your agent is able to get good? Reinforcement learning has a challenge. If it takes too long, then it may not be practical. It may not be viable, or it may actually not even be ethical to proceed down that path. And we can talk a little bit more about this. But all of these fall under the second umbrella in the environment. We need to have an environment that gives us reasonable action and observation spaces. All right, so we know the term transfer learning. You train in one context and then you want to apply it in another. The same concept applies also in reinforcement learning. So let's say you have an agent which is trained by interacting in one environment. Maybe you learn to fly in a simulated, in a flight simulator, and you would like to allow that agent to actually fly outside. Or you have a car, let's say you want to do autonomous driving, and you actually had your car learning to drive in a real car in Burutu. And then after learning and being able to being able to be satisfied with its performance, then you say you'd like to deploy that car to drive in Lagos. Now, most of us have had the experience of using a practice test or preparing for a practice test, and then when you go to the real exam, maybe you're wondering, hey, did I study? Well, that concept can exist as well in reinforcement learning. Now, flipping the script a little, what happens if we were not given an environment? Can you apply reinforcement learning in such a context? Of course not. But if you're not given an environment, in essence, that means that you as a designer, you as a machine learning practitioner, you now have to create that environment. And you're creating that environment by generating that Markov decision process. So you get to make the decisions. What does my state space look like? What does my action space look like? How does my reward function how is it implemented? Right? And there is not just one way to define these things. At the core, we need to have, and I insert this word, safe environments. So it's okay to make mistakes in the environment, because we do have this trade-off between exploration and exploitation. And maybe you choose a suboptimal action because you'd like to learn a little bit more about what could be. If your environment is the real world, let's say online learning or healthcare, clinical trials, there are serious ethical questions around giving a human being a suboptimal intervention or performing an action that you know is not the best. So this concept of being able to make mistakes is not the case for all environments. And back to the question of easy to interact with the environment, this notion of being able to run, let's say, one sequence of actions may take a few hours to evaluate. What if that costs more than the benefit that you can provide by learning something about that environment? So this is what I meant about, there are some real ethical questions in the domain of reinforcement learning that are on deck. So we need to think about these things when we talk about there's a need for safe environments. So if you do know things, and this is the last bullet here, a word on priors, if you know something about the environment, meaning you know where good evaluations should lie, instead of searching the entire space of actions, maybe you can reduce the action space, or you can reduce the observation space, thus making a problem that was technically intractable previously. Now you work on a smaller version of that problem, and now you're able to solve it in a manner that's more appropriate. So there are different ways that you could go about the process of making something that might not have been tractable. The final piece I'd like to leave you with before transitioning to Oliver is that there's this concept that, hey, I have a hammer and I'm looking for a nail. So when we're talking about reinforcement learning as a technique, is it the best option? We can't always make that assumption. Just as any machine learning technique, we should consider that there may be a different technique that can have better outcomes, either generate better results or generate results more effectively. So I would assert that when we're evaluating, we should consider at least two other methods. In this particular case, the same problem was addressed using 6 different implementations, 6 different algorithms. 3 of those algorithms were from the reinforcement learning family. And unfortunately, for the purposes of this figure, those Q-learning, Monte Carlo search, which is actually just speaking about a particular type of off-policy reinforcement learning, and deep Q-learning, which is a type of deep reinforcement learning. These 3 algorithms, of the algorithms considered, scored worse. Higher is better in this case. So here's something I'd like you to notice. Randomly evaluating options was better than using reinforcement learning in this particular context. That doesn't sound positive, right? You're wondering, hey, if I can randomly just pick something out of the air, why would I think about reinforcement learning? Well, there's context here. Let me also point out, see this outlier up here? Deep reinforcement learning was able to, in one case that was generated for this figure, find a much better solution than any of the other algorithms. So given enough examples, the RL techniques, especially the deep RL techniques, are likely to outperform. But remember, I made the point about sample efficiency. So depending on what the context of the problem that you're trying to solve, there may be options that are better. There may be options that are quicker. But each option has its trade-offs. There's a positive and there's a balance that we have to strike. So the 3 examples that I showed last time, rod maneuvering, which I indicated as something that could have had implications in terms of surgery, was one of the earliest. About 10 years later, we saw this example of autonomous helicopter flight. About 10 years later, 10 years after that, we saw the exciting work being done in the Atari universe. Things were easy. When you look at those environments, all of these environments were done where it was easy to sample because there were simulations being used. There was no risk to human beings if there was something that was wrong. So again, this concept of a safe space where you're able to sample efficiently, etc. Compare that on the bottom. If we were now talking about healthcare, so both of these are examples from healthcare. In one case, it's HIV treatment. In the other case, it's cancer. When an action is performed, it has direct implications on either a treatment plan or the potential outcomes a person can get. So in these contexts, we have to really walk that line quite gingerly because our algorithms can have a negative impact. But keep in mind, as practitioners, we have to be aware of these things, whether it's machine learning or other elements in the AI umbrella. This is something that we have to be aware of. So we have to be fully aware and conscious of the limitations of our techniques and what implications they may have for others. All right, so we can pause if there are any questions. I can start the chat as well as Oliver gets ready to do his presentation.
Okay, thank you so much, Sekou. There are already 2 questions on the chat group. There's one on the question and answer forum, and it was, how long is too long?
So the concept of how long is too long really depends on your domain. So for example, there are, in our case, in the context of malaria simulations, there are some models that take fractions of a second to give you an answer. There are other models that take 6 to 8 hours to generate an equivalent answer, just using a different mechanism. if you have to evaluate, let's say, hundreds or thousands before providing insights, one may really ask questions about which environment is needed to support the answers that are required. So in some cases, it may be easy just to say, given the time budget that I have, I will use the quick model, but maybe there's higher uncertainty in that context. Or I may say, given the level of uncertainty that's required to make this decision, I must use the expensive model. So there is no easy answer, or there is no broadly applicable answer to that question of how long is too long.
Okay, thank you so much, Sekou. Then there's another question here. How much noise is tolerable in an environment? Is there a threshold? That's from Ayobami Ade.
Ayobami, I know you're going to be disappointed. There is no even, for that question, there is no clear answer. It all comes back to what's the context? What's the decision that's being made? How much noise actually influences the answers that are generated through the reinforcement learning algorithm implementation? So you can't know a priori. You actually have to get in and see.
Okay, thank you so much. Then we'll take the last question. The last question is, okay, we'll just take two more questions and then we'll just move into the next session. How is reinforcement learning models? How are they evaluated? And then the other question is it possible to have a block neural net to learn the best to reward an action? So two questions for you.
Understood. So the short answer to the second question is yes, you can use neural networks to learn the best rewards for an action. In essence, what you're describing is something called, we can say, policy, learning the policy directly. The concept of how is the RL, I don't use the word RL model, we can talk more about that, but the concept of how the RL agent is evaluated is the same way that it actually, it learns. So you look at the rewards that it generates over its lifespan or over a fixed duration. And let me stop sharing and I can answer the last one typing.
Okay, thank you so much, Sekou. So, Oliver, I think over to you now. Okay.
Perfect, thank you. I'm just gonna expand my screen so that I'm in full view. So hopefully Sekou will be on the chat while I go through this. And yeah, we'll do the same and pause for any hanging questions at the end. Yeah, so what I wanted to talk about is people were posing some questions about the use of neural networks in reinforcement learning there at the end, whether it was to do some prediction on future reward based on an action, or more generally how we might be able to train neural networks with reinforcement learning. I'm going to focus on another supervised machine learning technique applied to reinforcement learning and motivate why this might be of interest to you and yeah, why it's a valid consideration for lots of real-world reinforcement learning problems, which is the application of Bayesian non-parametrics. Specifically, we'll talk about Gaussian processes. So yeah, rather than digging into the complete outline of the talk, you'll see this flash up a few times, and I'm just going to jump in to give some motivation in terms of machine learning model structures that we talked about a bit with Sekou, and yeah, then move on actually to bring in some of the content from bandits along with reinforcement learning together. So we had this discussion in Sekou's talk, so just a very quick refresher on this. We know that that supervised learning and machine learning, we have data with labels as an input, and we're learning a functional mapping to labeled outputs for prediction, classification, etc., where our critic or our error is some loss function against which we score our algorithm to the labels. In the unsupervised learning space, we're looking for some patterns or classes in the data, which doesn't have any labels, but may present some features or distributions against which we want to draw insights. And then we see reinforcement learning within machine learning, where actually we're interested in states and actions because the problem is temporarily situated, and we want to make these observations from a reinforcement learning environment and learn a reactive policy based on a reward signal or a reinforcement signal from the environment. And that reward signal, as we discussed, may be very intuitive or may be very problem dependent. And that's obviously an open question in the domain, because your supervision through this reinforcement learning signal, as opposed to a fixed label on the data, will obviously highly impact your solutions or outcomes. So we talked about reinforcement learning as
okay. Sorry, Oliver, please can you reshare your screen? It's blank on the side.
Okay.
Yes.
Understood. So
Okay.
I will stop sharing and reshare if people are being bothered by the black on the sides.
Okay, thank you. It's just blank here.
Okay. So let me try a different view. Let me share like this. Hopefully that will be better for people's views. Is that better?
Yes, this works. It's clear now.
Perfect. Thank you. Yeah, sorry if that didn't render so well on everyone's screen. I hope this view is better. So yeah, we talked about reinforcement learning as being specifically temporarily situated with regards to observations or states around a system and particular actions or interventions that can be performed. So for this purpose, I just wanted to dig into what that environment really is. And for any real world simulated problem, that environment's likely a mathematical model structure for a dynamical system. And dynamical systems models we can place into three groups, and it will become clear why we care about this shortly. But black box models are entirely data-driven phenomenological models, which is what we consider a machine learning model, a parametric machine learning model, which is entirely defined by the data, along with the Bayesian non-parametric models we're going to talk about, and it's learned in a supervised learning fashion based on minimizing a loss to some observations or labels. But the structure of the parametric model is not guided by any underlying physical mechanisms. So we're not describing any rate-driven equations or any interactions which have been generated through physical inference. Conversely, white box dynamical system models try and be entirely mechanistic and completely describe, accurately describe the underlying physical mechanisms of the system of interest, which makes them completely explainable as well with regards to the predictions the model generates with, and the particular mechanisms driving those. Dynamical systems may be described in a gray box manner, which mixes up components that are data-driven and mechanistic. So will motivate why we care about this. Now, for the purposes of reinforcement learning, we'll consider all models agnostically as black boxes. We don't actually care about perturbing any specific underlying physics in the environments. We just want them to act like the initial figure in terms of generating observations, states, and receiving inputs as actions, against which we can learn a reactive policy. So that means any reinforcement learning environment may also itself be learned as a black box or a machine learning model. So reinforcement learning agents are now posed, can be interacting with machine learning models as black boxes, as well as any other environment that describes a game or a physical system. What's important, and what we continue to labor this point, is for reinforcement learning, we're not only considering predictions of the system or the regression task, but we're considering interacting with systems that change over time based on actions. So the system or the environment that we interact with is not going to produce a static prediction, but is going to be influenced by our interaction with it, by the actions. So by looking at mappings between inputs and outputs from multiple machine learning models, these supervised machine learning models we know can generate predictions under uncertainty, and we'll talk about that with regards to generating predictions under uncertainty with Bayesian non-parametrics. And if we consider machine learning models as the environments that reinforcement learning algorithms interact with, we can exploit ensembles, committee insights across environments, hopefully to improve our ability to learn useful policies for real-world applications based on the fact that we had questions earlier of how much noise is tolerable within an environment. Other questions that could couple with that is, well, how good does my model have to be of the real world in order to learn a useful policy? We can try to reduce things like noise in the environment by looking at combinations across similar representative environments, if we can describe these as machine learning models, and we'll proceed to do so. So just a note on uncertainty quantification and noise. Uncertainty in predictions arising from the uncertainty in our model parameters or our environment is called epistemic uncertainty. And this kind of uncertainty may be better quantified, so our model can be improved, we know, in machine learning with more data or observations normally. We hope that any model would inflate its epistemic uncertainty in regions of little or no data, and we can reduce this in regions of more training data or observation. So epistemic uncertainty for any model we know may always be bounded on the model's ability to describe the phenomenon. So for any machine learning model, you know, you're not going to achieve a complete description of the system you're describing. Your loss will not go to zero at any point when you test your model. there'll always remain this epistemic uncertainty based on your model description. And then we try and capture uncertainty arising from inherent noise in the process, so in the physical system dynamics. This is an example of aleatoric uncertainty, and we can't get rid of this even if we make more observations of the system. In principle, we'll always have to accept that the future is uncertain. So in any environment description that tries to make predictions based on actions for a realistic real-world problem, we know that unless it's very well defined and the dynamics are completely deterministic, there is uncertainty about the transitions between states based on the actions implemented. So this leads us to posing simulator in the loop learning for reinforcement learning, whereby model simulations act to predict the future of a perturbed system, future state under actions. And we've motivated that for real world problems, this would be under uncertainty as well. Any decision-making agent may interact with simulators through online learning by reinforcement. And we've seen several examples, and Sekou talked about this as well, of success in reinforcement learning and how we evaluate reinforcement learning on benchmarks. So Atari gym environment is actually a common benchmark in reinforcement learning, whereby different algorithms will be compared on the variety of posed deterministic games for the Atari arcade environment. But we acknowledge that reinforcement learning has tended to avoid complex physical simulation models, which is the space that we're trying to work in. And as these are complex physical simulation models, I'm going to talk about how we might overcome some of the challenges of learning from these models. So now I'd like to talk about generating one-step predictions for control with online learning, specifically with regards to running simulations as bandits. So not yet talking about the full reinforcement learning problem, but we wanted to introduce these concepts in the one-step guys, so that then we can expand their application to multi-step learning or full reinforcement learning. So any bandit algorithm will select an action at time t and receive a reward. You can see what's missing from the full RL problem is an observation of states. So we call this a one-step decision because essentially we only have a single state for the system. So this bandit, which may have multiple arms, may be able to perform multiple actions and receive stochastic rewards from any physical simulator, it exists in a stateless or single state system whereby the initial conditions of the simulator just define that state and we return to that. So in this case, the search for an optimal policy would define a single arm which maximizes our reward over repeated pause as we pose the optimization problem of finding the arm that gives us the highest cumulative reward over training. So in this case, I talked about stochastic rewards from arms. We could define a simulator as an epidemiological model that takes an action as a set of posed interventions and runs it over a prescribed time. And these actions will return stochastic rewards distributed by these box plots. And we can compare different actions. The goal of the bandit algorithm will be to both explore and exploit high-performing actions. So take sufficient samples to characterize the distributions on the arms in the case that there aren't too many arms, and continue to gather rewards from high-performing arms. I talked about this being a stateless transition, whereby we could think of this as just containing a single state, and that transition comes back to the initial state of the system. So now if we expand to interventions as actions across an action value function, Q of A, sequences of actions can be seen to iterate and improve our inference of a continuous action function. And don't worry, I'll talk about what inference is being done here based on the rewards with regards to the Bayesian non-parametric approach of the Gaussian process. So that's what I want to get onto now. Specifically, how do we use these supervised machine learning processes to help improve our function approximations and actually provide predictions of future state from simulations. So machine learning is applied to the task of predictions, and we could call this a surrogate model description if we want to learn a new machine learning model based on some underlying dynamical model, which is generating data for us. And a machine learning surrogate model description can make sense where the underlying simulator is computationally expensive, and we want easy ways to share and combine the model in a black box fashion. If we do functional approximations of our simulation models, then we can achieve quantifications of uncertainty from those simulators as well, but that may not be present just from running the model itself. And we'll specifically talk about model calibration or learning of model parameters to improve predictions. So this actually comes to the point of AutoML and how do we deploy machine learning algorithms for machine learning tasks. If we have exposed parameters, we can actually use these techniques to learn or calibrate or improve the underlying models for predictions. And we care about predictions in reinforcement learning because we want to know what the future looks like under our interventions or actions in order to be able to develop effective reactive policies to the control problem. Here I've given the example of COVID-19 disease model developments whereby you could think and try and motivate the ensemble or combination of these different models for improved predictions as well. Right now, the CDC in the US just takes a linear weighted combination based on the expected combination of the different model votes from the predictions they generate and the outputs. But perhaps there may be more intelligent ways of combining predictions from multiple models, again, that allow us to accurately quantify uncertainty in our future predictions, and also to plan from these models about what high-performing future policies could be. Obviously, we care about generating optimal control plans for problems like COVID-19 under uncertainty, where multiple predictions may exist for a highly uncertain real-world environment. So Bayesian non-parametrics. A non-parametric Bayesian model is one who essentially has infinite parameter space. So rather than a neural network, which has a finite number of weights that characterize its structure, we define a non-parametric Bayesian model describe a probability distribution or prior over an infinite dimensional space. So this infinite dimensional space essentially describes the prior family of stochastic processes which may best describe our observations. So here we're talking about a infinite dimensional space T that defines trajectories of a stochastic process, and we try and impose a Bayesian model structure on this so that our observations can highlight what the most probable trajectory through this infinite dimensional stochastic process may be with the Gaussian process. So just to talk more practically with regards to the technique, specifically here we want to perform regression using Gaussian processes. And Gaussian process regression is a well-known statistical learning technique whereby we define a mean function and a covariance function based on this expected trajectory across infinite dimensions from our observations. So this Gaussian process is specified as a distribution across possible mean functions and covariance functions. We can represent any stochastic simulated function here, y, such that it contains samples which are normally distributed around a zero mean and their own covariance function with some noise added to the stochastic process, which allows us to specify a joint distribution between our observed training values of x, so our training data, and what our inferred function values are when we perform the regression at test locations under our prior assumptions that we can define the stochastic process as an infinitely dimensional Gaussian. So given a set of training points and test points for the regression, we can learn a covariance function across these pairs and construct a conditional distribution based on the observations to perform our inference on the test points. So in the case of a zero mean functional prior, which essentially says that our expected value from our function is zero everywhere, unless there's evidence to support otherwise. And this gives us a direct solution for defining a Gaussian process under various kernels which specify the local smoothness of the functions and interactions between our training data. I'm not going to talk specifically about possible kernel functions. I just wanted to give a quick overview that we're able to specify features of these kernels that can be learned through an optimization scheme to best fit the observations across tasks by maximizing a marginal likelihood or log marginal likelihood in this case. So practically, what this means is we can either place some prior assumptions on values within our Gaussian process inference based on domain knowledge of the problem. So in this case, length scales across which we know there are interactions between our observations, our expectation of noise in the underlying problem, and also what we want our kernel variance to be, so how uncertain we should be where we don't have any data or support. The two examples here just show the difference between a judicious choice in the Gaussian process parameters and what can be achieved with an optimal fit to 4 training points of a noisy epidemiological function in this case. You can see the main objective here is to generate inference at our test points that capture some notion of uncertainty. So we have a bold line that captures the expected value, and then we have bounds with regards to the upper and lower confidence intervals. How our covariance function describes our 95% confidence interval for an inference at any points that have not been observed. I'm keeping an eye on the time and making sure we don't go over. I'm aware we've almost covered my slot just on the Bayesian non-parametrics, but hopefully we can continue on this thread. In the case of reinforcement learning, instead of an abstract function inference based on a 1D input variable that we had the example before, we actually want to consider some simulated action and what the future reward could be from that action. So in this case, we can define an action value function Q of A as the expected reward given the action taken, which in this case would be the learned mean function of the Gaussian process, which consequently has a covariance function defined K of A and A dashed. So given a Gaussian process learned that specifies these mean and covariance functions for the action value function, we just change notation slightly to talk about what our inferred value under uncertainty of our action value function would be given stochastic scalar rewards from the underlying dynamical model which we're observing. So again, we can apply our learning scheme to infer our posterior distributions on our mean and covariance functions, given the actions taken and the stochastic rewards received. I won't go too much further into this at this point. I just wanted to note that a common kernel form for our covariance function that we use in modeling of physical systems is the Matern kernel. And much like Sekou's talk, I provide all the references and slides for the deeper examination into this material and refreshing it. So in the previous example, instead of just having single banded arms, which are combinations of interventions, we can now do regression across those that aren't observed using the Gaussian process structure to do inference across our action value function, which in this case gives us a smooth value function in terms of the reward improvements across our 2 intervention components of an action for the bandit task. On the left, you can see the expected value, and on the right, we're trying to quantify the uncertainty in that value function with regards to the upper bound. So we're not uniformly certain with regards to the actions that we want to take. So it's not simply a case of maximizing our expectation necessarily in the decision-making task, because we may want to choose options where we are more certain about the outcome. So the darker blue regions on the right, in combination with the expected value of the outcome. So at this stage, I want to include material on how we can use this supervised Bayesian non-parametric regression, not only for doing inference across action value functions for the bandit task, but extend that to learning model parameters for predictions. So we've said models are black box environments, and we want to improve our ability of these black box environments to describe the real world. So we can actually pose a set of exposed parameters from these models with regards to the prediction task, and try to improve the model's ability at prediction. Essentially, like you will do in the optimization of any machine learning structure, I just want to extend the application of Gaussian processes as non-parametrics with regards to Bayesian optimization. So for any optimization task, we have an objective function, which is potentially unknown, nonlinear, non-convex, non-derivative, and stochastic. So in this sense, it makes there's a lot of utility for us to learn some surrogate model of the underlying function, because we can't do traditional optimization tasks on that function. And any candidate solutions to optimality for that function may be high dimensional as a set of possible actions, but for Bayesian optimization and Gaussian process inference, we want to restrict those numbers to be in the order of less than 20, less than 10 for the ability for these techniques to be analytically tractable. And evaluation of the objective function will normally be very computationally expensive for the application of these approaches. As you can see, we generate a reasonable functional description based on limited samples from that function, and quantify uncertainty with regards to the bounds in that function. So this makes a lot of sense for applications where returning evaluations from the function are particularly expensive. So we can frame the process of exploring solutions to the optimization problem using Bayesian optimization as simply maximizing this objective function against which we'll learn a Gaussian process surrogate. So in algorithmic form, we want to maximize, make the maximal decision under some acquisition function of our observations based on the input features and the learned Bayesian non-parametric model behind that, and then run a model simulation at the selected maximum point to provide a subsequent observation, which we can now update our surrogate model with. So update our Gaussian process posterior, specifically the mean and covariance functions. In order to achieve this from our Gaussian process surrogate model, we have an acquisition function that acts on that surrogate model. And I'll take the example of expected improvement. And this can be thought of as looking to maximize the difference between our best observed loss, where we believe that the best function evaluation to be based on our previous observations. So in this case, we may have some prediction mean, and we've made an observation where we believe our current best value to be, and we want to combine also our uncertainty in the location of that. And I think this concept is maybe best highlighted with regards to the example we had previously. So just using the exploration parameter from the Gaussian process model that we learned previously, we can see that in this case, our expected improvement is maximized on the right with the orange line, where the values of not necessarily our expectations of our solid blue line are maximized, but the contributions also of our uncertainty with regards to the variance lead for our subsequent sample to be chosen on the far right. So a sequential scheme would then run this, would then run the parameter value, so x equals 1 through the dynamical model and receive an observation, which would allow us to update our surrogate model and consequently choose a subsequent location to sample so that we can improve information around the location of the optimal solution to the underlying function. What we've done just as a practical application of this is applied it to dynamical system models of disease spread for COVID-19. So in this case, taking a set of parameters for a compartmental model, which is described by a system of linear differential equations, and the accompanying rate equation, the accompanying rate constants can be learned based on observations. The yellow dots across different US states here that tried to fit the model predictions based on the model parameters, now to generate a black box environment that a reinforcement learning agent can interact with, much like was exposed on the AI challenge or as part of these efforts. You can see that if we're able to improve our dynamical systems ability to describe the real world with these techniques, we can improve the quality of the control policies learned from any environment that tries to describe it. The environment being, and the environment capturing these calibrated systems. As a sequence of searches coming back to the initial stage. So this parameter learning would be another example of a bandit problem, whereby the sequence of decisions is your mixture of parameters which allow for your loss to be minimized in fitting your dynamical system model. So the selection of the parameters is principally also a bandit task in finding the highest performing arm, which describes the parameters for your model, which produce the best predictions into the future. Now, this changes, of course, when we want to do multi-step predictions and control with really what we pose reinforcement learning for. So we've talked about the multi-armed bandit problem of posing an action. So to stick with the epidemiological models, that could be a single combination of interventions that's applied in a deterministic fashion until the end of the model simulation and receives some stochastic scalar reward. Or it could be a combination of model parameters that best optimizes the model's ability to perform predictions based on available observations. The reward in this case being a loss between your observations and your model predictions. Now, if you wanted to scale this as a contextual bandit problem, perhaps you want to do what we showed of similar tasks across different locations, and that could be considered as a contextual bandit where the location describes the different state, or and in this case it's not a state that leads to that is perturbed by the action, but it's just some context about the problem which can help you optimize the learning process. So if you want to make a decision for a similar problem in different locations, understanding what the location, what the context is that makes up that location would be considered the state for the contextual bandit problem. And then we come full circle back to full reinforcement learning, whereby our actions perturb that state. So of course, learning model parameters for different locations is not a full reinforcement learning problem, because when we learn a model for one location, it doesn't transfer us to another new location. Whereas learning a sequence of decisions in the same environment does constitute this full reinforcement learning problem, where rewards, as we said, may be delayed based on the action, but the action will lead us to some transition of state or observation that we make from that environment. So we've seen this figure already, that again, our environment acts as a black box description of a dynamical system that takes inputs of actions and outputs subsequent rewards and states. The rewards can be delayed. Yeah, I think I've covered that quite a lot through the talk. So the jump now is to say, well, given any description of the real world, how do we, in the form of a dynamical system model, how do we make it conform to this structure that means that the actions will perturb the state and lead to different rewards being observed by the agent, and subsequently expose them to reinforcement learning approaches. In this case, instead of learning a single surrogate model with a GP, we need to impose some structure to the problem. And the structure that we use is a tree-based structure. That means that there are branches dependent that are conditioned based on the actions taken. So the tree structure tries to learn a state transition, which would be the probability of transitioning to a particular state given the action taken, and a reward function, again, which will define what the likely reward received is in a particular state, given the action taken, or given the state and action taken. So as opposed to just a single bandit, in this case, we need to be able to define descriptions where our models describe what the reward looks like for any particular state and action pairing. And of course, this is a non-trivial task from any dynamical system description. I think with looking at the time and wanting to preserve time for questions, I just want to quickly highlight that we use a technique called Monte Carlo tree search to decompose episodic simulation results into a tree structure at which each node can describe a value function for a learning agent. There are four steps to this approach, but I don't think I'll be able to go into this so deeply, but just give it as a reference point for a typical technique or a canonical technique that's been used in, well, developed extensively for the game of Go, so very high search space problems, state space problems. Okay, so if we impose a tree structure on our epidemiological problem and compare the results of the best multi-step policies, so the best reinforcement learning policies that can be learned as opposed to banded policies or deterministic policies learned through banded approaches, we see clear benefits in being able to decompose decisions into sequences of actions that are stochastic based on observations from the simulated environments. In this case, the red and blue dots, we can see that if we want to achieve a particular malaria prevalence ratio, parasite prevalence in our population, we can do this at reduced cost given the set of actions available if we take this as a sequential decision-making task as opposed to a single step bandit decision-making task. So perhaps a few of you had the chance to interact with our competitive framing of making a 5-year decision in malaria control. This just sets out the problem, and I wanted to quickly talk about the fact that, yeah, we've received different solutions where people will frame this either as a multi-armed bandit problem. You can see in the bottom left, different approaches used Thompson sampling in a multi-armed bandit and then changed that to a later contextual bandit that was aware of the year in which the decision was being made. Others used models learned through Bayesian optimization to apply model-free reinforcement learning in the form of Q-learning that we've talked about previously, and also tried to do things like particle filter estimation to improve the knowledge of the underlying environment description. So let me jump to conclusions of what I tried to cover and ideas of how you might want to extend some of these into your project or work. So we've discussed reinforcement learning methods applied for either single-step banded or sequential reinforcement for reinforcement learning control and planning problems from real-world simulations through the application of Bayesian non-parametrics to perform approximations of expensive dynamical system models for the purposes of predictions. These surrogate prediction models that have been generated for sequential decision-making tasks could actually be shared for multiple different approaches to the model-free learning problem through competitions and machine learning challenges. You may have interacted separately in platforms like Cindy and know the kind of numbers of competitors who may interact with these problems and the need for a computationally efficient platform to be able to query sequences of decisions from these environments, which we acknowledge beneath them are computationally expensive. And then finally, by allowing the use of heterogeneous model structures, so dynamical model structures, we can generate useful predictions under uncertainty through applying Bayesian optimization if we have observations for the prediction task. So we can make use of, we're agnostic, we can make use of various model structures in a black box fashion to produce environments which better describe uncertainty of the underlying processes and can be exposed to reinforcement learning agents. So where might you want to take some of these concepts? Always interesting to pose or think of your own uncertain physical system where the search for an optimal policy can make sense. So where a temporally situated decision can have high impact. And would it be possible to learn a non-parametric model which describes the system in a data efficient manner for the purposes of applying model-free RL or and testing out things like Q-learning? And why might we generally want to look for data efficient machine learning approaches in sub-Saharan Africa? And just as an overview for the talk, that's why I wanted to cover or at least introduce the concept of Bayesian non-parametrics as something you may want to consider in different machine learning tasks as well, not just reinforcement learning. Great. At this stage, I will try to look at the questions screen if there's anything there.
Thank
Okay.
you so much, Oliver.
Okay.
Go ahead.
Don't continue.
Okay, thank you so much. Thank you so much, Oliver, as well. Thank you. I think the guys been doing a good job of just answering the questions in the Q&A section. So most of the questions have been answered via text.
Fantastic. Yeah, just scrolling through as well.
So one question that I have, not for the attendees, but for organizers is that, there was a question about whether there can be a hands-on activity. I think we can probably talk about how that can be hosted. We had one running, I guess until this week, but I think only one person submitted anything. I don't know how many people actually signed up, but we're open. Everything that we shared via that activity is actually something that can be done without actually having to sign up as well. So we can do that too. We can just work with you to make that possible.
Okay, sure. Thank you so much for the advice. I also noticed the comment as well. So something I've already taken notice of, and we'll reach out to you definitely.
Okay, cool.
See how we can get that done. So thank you so much. Really appreciate the time we've spent. Can we just in the chat section just appreciate our instructors for today? So if you're still following those, appreciate. You can just do a thumbs up in the chat section and just say thank you. And if you have any questions, I've seen a lot of questions regarding the availability of the recording. We would make that available next week, so you would just check out. Probably I'll send you a mail to alert you of that, or just subscribe on our YouTube channel, because this will be posted on YouTube, so that once it is out, you would also be informed. By the way, thank you so much, everyone. Thank you so much for coming. If there are no questions, I think we'll just end the sessions right here. Thank you so much. Yeah, someone saying great content. Thank you, Remy and Oliver. Thank you so much. Do have a wonderful evening. Will there is any other thing that you want to add?
Thanks to everyone for joining. Thank you, Sekou. Thank you, Oliver. I understand that some people, the video will be available, like Sheon said. You can watch previous videos so that you, by Data Science Nigeria. Thank you, everyone, again for joining. I hope you had an interesting time. As always, DSN, we bring the best people in their field, and we are glad that Sekou and Oliver decided to give of their time. So I'm looking forward to the weekend too. It's Friday.
Thank you, everyone. Have a great weekend too.
Thank you. Bye.
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 Bye-bye.